Hi, welcome to Unit 9 in AP Calculus. This unit is titled Differential Equations. Solving differential equations is a really important skill to have to develop in calculus, and it's so important that usually people in the STEM field will end up taking 2 years of courses simply about solving differential equations. Well, we certainly won't be going that deep into it. We're going to be spending just 4 lessons on it, but hopefully we'll lay the foundation for future learning in those classes. All right, so let's start with just some definitions that I imagine you can guess what they mean. We are going to say that a differential equation is an equation that relates dy, dx, y, and x, or even possibly d2y dx squared, y prime or y double prime, but it's some sort of equation that involves those kind of things. And a slope field, or what some would call a vector field, but I'll just say the words slope field, is a graphical tool to represent these relationships. So let's take a look at one. So in our first example, we're given a differential equation dy dx is equal to y. We're going to represent this differential equation using a slope field. Making a table of values is a good idea to help you organize your work, but it would be difficult to make a table of values for every single point on this graph. So usually we just want to do enough to get the pattern. So I'm going to start with x equals 0 and y equals 0. Well, it turns out that if y is equal to 0, dy dx is equal to 0. And it doesn't matter what the x is, the dy dx will only be 0. Let's take a look at, say, when y is 1. When y is 1, dy dx is 1. And again, it doesn't matter what the x is. What about when y is 2? When y is 2, dy dx is 2. Likewise, when y is negative 2, dy dx is negative 2. And again, it doesn't matter what the x is. So we could put in anything we want there. So let's start filling that out. First of all, we realized that when y is 0, dy dx is 0. So we're just going to show a little bitty slope here. Just a little tick mark indicating that everywhere the y is 0, the slope is horizontal. Then when the y is 1, we'll do a little slope. And notice I'm doing it at the up 1 over 1 kind of ratio, just pointing right here, like so. And I've already figured out the pattern, so I'm not going to go and keep making more values on my table, although I certainly could. I could make a whole nother column and, start doing it for more and more x's. But I see the pattern, so I'm just going to go with it. And then as y becomes 3, we're going to get even steeper. And I'm just kind of trying to represent it. You can imagine why slope fields are so often generated using a calculator or some sort of tool like that. Okay, I think that's pretty good for the top half. Oh, that one needs to be. But we know that it's always getting steeper. I didn't always draw it that well, but always getting steeper. And here's negative 1s. And there'd be slope fields in here as well. We could go in between the 0 and negative 1 and show halves if we thought that it would help us get a picture, but we don't have to. All right. Now, occasionally, AP students might be asked to construct their own slope field. Usually, it's a pretty small value. I don't usually see the grids this big. And other times, you're already given a slope field filled in, and you'll have to interpret it. Or I've seen a lot of questions where you are given a multiple choice question, and you have to match a slope field to an equation or an equation to a slope field. All right, so we've generated a slope field. So what does this tell us? Well, let's take a look at a couple of questions that we can answer. Let's draw the curve for the solution to this differential equation through the point 1, 1. So what I'm going to do is I'm going to try and estimate the graph of the solution to this equation that goes through the point 1, 1. So the solution to this differential equation is an equation where it would make this statement true, that if I took its derivative would be equal to the y coordinate. Well, I can see that at a point on my solution curve at 1, 1 would be directed like this in the neighborhood around 1. But when it gets over here, it's going to start getting steeper. So it's going to be getting more and more steep. All right, and then this is going to keep curving and getting steeper like that. And again, I'm just kind of estimating the solution. Now, as I come back this way, though, these slopes would get flatter. Something like this. Okay. And there we have it. Now let's draw a curve for the solution of this differential equation through -2, -1. So now we're going to do -2, -1. And I'll use a different color for this one. I think maybe an orange would be good. So I'll just indicate that I'm using orange there. So -2, -1, that'd be over here. So this is going to be, this is supposed to be a slope of -1 here. So it's going to be coming down a little faster, I think, than the other one because it's over here. And then, something kind of like this. So you can see that the shape of the curve seems to vary greatly based on the solution, the point that the solution has to go through. That seems to make a big difference. All right, one more I want to look at. Example 1.1 demonstrates the shape of the curve of the solution to a differential equation. And it shows, like we discussed, that it can vary greatly based on a point the solution contains. A given point to the solution contains is called an initial value. And as we see, initial value can really make a difference. Such problems involving differential equations and initial values are called initial value problems, or IVP. And in example 1.1, the solution through the point 0, 0 is a very special solution. Let's take a look at that. What would happen if I used this point here, or in fact any of these points on this line? Because the slope there is 0, it's going to stay flat. And this ends up being just a flat line. So this is an important point, that if we want to have anything really interesting about our curve, we needed to go through some point not on that line. That is called the equilibrium solution. Y equals 0. And some differential equations have multiple equilibrium solutions. All right, let's take a look at a slightly more complicated differential equation. This one here, we have dy dx is equal to the sum of x and y. So we can make a table of values again, but I'd say, well, let's make a table of values, just a little bit of one, just to help us get the idea. And then you can say y prime or dy dx, whatever you want to say. So I'm going to start with 1 and 0. The point 1, 0 would have a dy dx of 1 because 1 plus 0 is 1. Likewise, 0 and 1 would also have a slope of 1. Let's go ahead and plot those on our graph. So this is a slope of 1, and this is a slope of 1. Well, let's see. Wonder if we can figure out what else would have a slope of 1. Well, if our x was 2 and our y was -1, that would also have a slope of 1. So 2 and then -1 would be here. And what about 3 and a -2? That would also have a slope of 1. Likewise, -1 on the x, +2 on the y. So do you see the pattern? So you can see all those, everything kind of on that line there seems to have a slope of 1. Now, the point 1, 1, 1 plus 1 would be 2, is going to have a slope of 2. 0 plus 2 is 2. -1 plus 3 is 2. And you can see, again, we have this pattern that we can use to help us figure it out. I bet you can imagine what 1, 2 is. That's a slope of 3. That's even steeper, right? 2 plus 1 is 3. So that's what's happening. We're getting steeper and steeper, but along this kind of diagonal shape here. Now, if I plug in 0, 0 to this equation, I get a slope of 0. Likewise, if I plug in -1 for x and 1 for y, I get 0. So here's that slope of 0 that we know is so important. And then what happens before that? Well, at 0, -1, we get a slope of -1. At -1, 0, slope of -1. All of these are slopes of -1s. And then these would be slopes of -2 And you can check the math for me if you want. So we have a similar situation that we had before. We have this line that seems to be kind of flat, and then everything else is going away from it on each of the different sides. But this time that line is not something simple like y equals 0. It's a little more complicated because it's a diagonal kind of feature. And then these are getting really vertical over here. Okay. And we could finish them out over here as well. So that's the idea about what this graph is doing. Let's draw the solution through 2, negative 2, comma 1. Well, there's negative 2, comma 1. What does that do? Oh, no, I'm sorry, 2, comma 1. 2, comma 1, that's over here. Well, that is going to curl way up like that. But coming over here, this is going to be flat, flat, flatter, and then go something like this. So it'll be something like that. Well, what about at negative 2, 1? What would that be? Well, that's this unique situation where everything on this line has a slope of negative 1. And so that line is going to go just like that. Had it been to the left of it, like at negative 3, 1, then we would have expected this curve to do something like that, but it didn't. All right, let's take a look at another one. I have dy dx is equal to x over y. And again, we can make another table of values. First of all, though, I want to point out that if x is 0, then the slope is 0. So everywhere the x is 0, the slope is 0. I'll use red again for my slope fields. I kind of like that. So 0, 0, 0, 0. But here it's actually undefined. In fact, it's very undefined. It's 0 over 0. It's indeterminate. So I'm going to leave that blank. Now notice whenever the y is 0, x over 0 is a vertical slope. That's undefined. Not 0 over 0. That's indeterminate. We don't know at all what that would be. So I'll leave that blank. All right, let's talk about what would 1, 1 be. If I put in 1 for x and 1 for y, I get a slope of 1. And in fact, all of these points for the x and y is 1 are the same. All a slope of 1. And these are all slopes of negative 1. And if I plug in 2, 1 to this equation, I get dy dx is equal to 2 divided by 1, which is 2. 3 divided by 1 is 3. 4 divided by 1 is 4, so it's getting steeper going that way. This is 3 over 2. And this is, again, a slope of 2. So it's kind of like that. 2 divided by negative 1 is a negative 2. Then this is a negative 3, negative 4. That's another negative 2, negative 3 over 2. So you can kind of get the idea of what's happening here, right? 1, 2, that's a slope of 1/2. So like this. And that's 1/3, and that's 1/4. 2 over 3 is 2/3. 3 over 4 is 3/4. So everything's kind of being pulled towards these diagonals. I hope you can see that. This one's negative 1/2, negative 1/3, negative 1/4. This one here is this negative 2 again, and then this is a negative 3. So we can kind of start to see the shape come out, right? I'll just kind of fill these in. There we go. And I think we've got a good slope field set up. So what happens if our solution goes to a point negative 3, 1? Well, if it goes to the point negative 3, 1, we know that it's going to start like that. But then when it gets here, it's going to be pulled vertical, which means it's then going to be pulled back this way and go something like this. Doesn't look like it's going to be a function at all, does it? And it turns out it's actually a hyperbola. It's got these asymptotes that are diagonal that it's being pulled towards. How about the point 1, comma 2? Where would that be? That would be up here. I'll use a different color. I'll use green. 1, comma 2 would be up here. Again, we're pulled towards these diagonals that we filled in here. And then this is where it'll be flat. And then it'll be like that. All right, let's try x minus y now. So if at x minus y, if I plug in 0, 0, I get 0. If I plug in 1, 1, I get 0. 2, 2, I get 0. 3, 3, I get 0. So all of these end up being zeros. If I plug in the 1, comma 2, I get a negative 1. 2, comma 3 is a negative 1. 3, comma 4 is a negative 1. 0, comma 1 is a negative 1 because I'm subtracting those y. So all these are my negative 1 slopes. If I plug in 1, 0, I get positive 1. 2, 1, I get positive 1. So you can see we're getting a kind of an unusual kind of shape here. Okay. But we could kind of picture a curve coming down, flattening out, and then going out like that, right? Let's try 2. What if I plug in 2, 0 for x and y? 2 minus 0 is 2, so that's steeper. 3 minus 1 is also 2. 4 minus 2 is 2. So I think we could see that we have this diagonal of 2. Then this is going to be all of these when we evaluate to a slope of 3. And all of these even more steeply to a slope of 4. And so forth, getting steeper and steeper and steeper. How about 1, 4? What would that be? 1, 4. If I plug in 1 for x minus 4, that's a negative 3. What about 2, 4? That's a negative 2, not quite as steep. And 1 minus 3 is a negative 2. So I think we can see the pattern. All these are going to be negative 2s. All these are going to be negative 3s. And then these lines of whooshing, if you will. We're showing this motion, this very kind of graphical idea of motion sweeping in. What would negative 2, 2 be doing? It would be going down like that, right? And then where does it go from there? Probably down here until it flattens out, and then it's got to go like that. So something kind of like that. How about 0, negative 1? Well, that's that weird one again. 0, negative 1 is going to stay right here at a slope of 1, never changing, always being an equilibrium solution. Okay, you've got some practice problems to do. Practice 1.1, A and B. And then I want you to study differential equation and try and just draw the solution through it. So you can see I'm giving you some differential equations for you to look at. And we've got still just a few more to do. So I want you to pause the video and try each one of those in your own little notes, and then we'll go over them. All right, let's see how you did. I dropped my little pin here. Okay, so we're going to make our slope fields. And I will start by realizing that the denominator of this fraction for my slope is y. So that means that whenever the y value is 0, my slope is going to be undefined. Or more specifically, whenever the x value is not 0 and the y value is 0, I'll have a vertical slope. I don't know what's going to happen at 0, 0 because that's indeterminate. Next, I'll notice that whenever the x value is 0, as long as the y value is not 0, 0 divided by any other number is 0. So all of the points have an x coordinate of 0 have a horizontal slope because they're 0. If I plug in 1, 1 for x and y, I get a slope of negative 1. Likewise, every time the x and y value are the same number, I'll get that slope. When the x and y values are the same absolute value but different signs, I get a positive 1. Here I'm back to my negative 1 slope, though, on this side. And then positive 1 here. If I plug in a 2 for x and a 1 for y, I'll be dividing a negative 2 by 1, which means this will be slightly more steep. And in fact, it becomes just more steep as I move out. And likewise, but in the other direction here. If I plug in 1 for x and 2 for y, I actually get a negative 1/2, so a little bit less steep. And I think we can kind of imagine what's happening here is we have this big circular, kind of almost like a hurricane kind of shape, right? I think you could even imagine what the solution to this differential equation must be. It has to somehow be related to a circle. And indeed, it is. Okay, let's go ahead and fill in. The point through -2, 2 would most likely look something like this. Some sort of curve like so. Now, if it's a function, it would only be part of this curve. But if it's just the equation, it would look something like that. Okay, what about the next one? dy dx is equal to x. So when x is equal to 0, again, I start by thinking about that. When x is 0, I have a horizontal slope. So all of these are horizontal slopes. When x is equal to 1, I have a slope of 1. And then we're going to get steeper as we move this way. And steeper still. Back here I have a slope of -1. And this would not be a difficult differential equation to solve. And in fact, we could easily just integrate both sides. And you can see that the solution to this is x squared plus some value c. And that value c is determined by where the point is that we are given, our initial value that we have to be going through. But this is a nice exercise in making a slope field. So through the point 0, 2, we would expect this curve to make some sort of parabola like that. All right, practice 1, 2. Study each differential equation and its slope field. Draw a solution curve through the given initial point. So this slope curve is y prime. We know y prime is dy over dx is equal to x minus y. And you see it's been drawn for us. We could check it. For example, this point here, 1, 0, would have 1 minus 0 is 1. 2 minus 1 is 1. And so forth. 0, 2 would be -2. So, but where would -1, -4 be? Right here. So what shape can I expect there? Well, just from here, I usually just start by drawing whatever the slope field is, because that's basically what that's the behavior of the curve in that neighborhood. And then we're going to be coming towards here. And as we're getting closer and closer and closer, we're going to end up getting flatter and flatter and more like that curve right there. So it ends up having this kind of shape. Let's take a look at the next one. dy over dx is equal to y squared. Let's take a look at through the point 1, 2. Well, the point 1, 2, we're going to behave just like this. And I think you can see that things are going to be going upwards very quickly. And then when we come down, we start to at some point flatten out. And since these slopes are all flat, it must flatten out as it gets closer and closer and closer to them. What about through the point 3, -3, -2? Well, that's a very different situation. In this situation, we're going to flatten out below the x-axis, but then approach it like so. All right, let's take a look at this problem. Consider the slope field for the differential equation dy dx is equal to sine pi over 4y. If y equals f of x is a solution to the differential equation with an initial value of f of 1 equals 1, then evaluate the limit as x approaches infinity of f of x. All right, so we've been given a differential equation, and we've been given a slope field. And we were told that the curve y is equal to f of x is a solution to the differential equation with an initial value of f of 1, meaning when x equals 1, y equals 1. f of 1 equals 1. Let's draw the curve and see if that helps us answer the question. Do you see? They're kind of hard to see, but these are some horizontal slopes here. So again, we're going to expect that the curve must flatten out over here. But then it starts to flatten out again going this way, towards again this horizontal slope. So it must be bounded between those two. So what is the limit as x approaches infinity of f of x? Well, it appears to be the number 4. Okay, let's take a look at this slope field. A little bit more detail here. Going from 0 to 0.5, we have quite a few slopes. The slope field for dy dx equals the absolute value of y times 1 minus the absolute value of y is shown below. If y equals g of x is a solution to the differential equation with the initial value of g of negative 1 equals negative 0.5. So negative 1 for the x goes to negative 0.5. Evaluate each. Okay, so we're going to be doing some limits, so we need to get a curve. So we're going like so, and it looks like we're going to be flattening out towards this kind of point here. It looks to me like we must have a horizontal slope here. Can we confirm that? Can we confirm that these slopes are 0? Well, that's part of the reason why we're given the equation. If y is 0, we sure as heck get 0, don't we? So we must be approaching a flat line. And once we hit that flat line, we're not going to go up any further. So, and as we get closer and closer and closer, our slope gets smaller and smaller and smaller. Likewise, we seem to have something happening at negative 1. That if we end up with a y value of exactly 1, we get a slope of 0. So as we're approaching 1 going this way as well, giving us that kind of shape. So the limit as x approaches to infinity appears to be 0, but the limit as x approaches negative infinity appears to be negative 1. All right, and I think that is a good place to stop, and that's the end of this lesson, and we'll pick it up in lesson 2. We look at how to solve these things. I'll see you then.